As we've seen, the magnetic force relies heavily on the vector cross product of two vectors. And so let's review that a little bit. I actually put that also in the reading assignment for today, and let's review it pretty briefly. You should have seen the vector cross product last semester in regards to torques, especially. But let's just review quickly so that it's fresh on everyone's mind as we start to work some problems in this regard. Uh, but first thing, let's remember there's two kinds of ways that you can multiply vectors. One is the dot product or the scalar product, and that's A dot B here for two general vectors. Theta is the angle between them, and the dot product is defined to be the magnitude of A times the magnitude of B times the cosine of the angle between them. And this side is just a number, it's a scalar. Yeah? And so it's aptly named as the scalar product or dot product as well. But in any event, uh, when you multiply vectors using the dot product or the scalar product, you get just a number out of it. You don't get a vector out of it. The vector product is a true vector. It's a way to multiply two vectors to get a vector. And so it's well named too, in that it's a way to multiply vector A and vector B to produce a vector. So the result of the cross product is to produce a vector. And the magnitude of the result of the multiplying those, this vector C, is the magnitude of AB times the sine of the angle between them. And the direction is that given by the right-hand rule. And I'll let you read about that, but it's the same right-hand rule that was introduced with torques. It's convenient to do things sometimes in unit vectors, and particularly get a multiplication table for it. And remember, if I have a regular Cartesian coordinate, so excuse me, excuse me, the unit vector I hat points in the along the x-axis in the positive x direction. J hat points in the y-axis in the direction of positive y, and k hat points in the positive z direction. And they're all unit vectors, so the magnitude of each one of those, and I always put a hat over the top to indicate the unit vectors, the magnitude is 1. So if a vector gives information about the magnitude and the direction, and unit vectors all have the same magnitude, I don't get any information there in terms of anything on a unit vector. So all of the information provided by unit vectors is simply a direction. I can take any cross product, I hat cross I hat, for instance, and I can compute what the magnitude of the resultant vector is, because it's the magnitude of the first times the magnitude of the second times the sine of the angle between them. But if I have two unit vectors I hat, they're parallel, and so the angle between them is 0, and the sine of 0 is 0. Alternatively, if you have two unit vectors I hat cross j hat, then the magnitude of it is the magnitude of I hat and magnitude of j hat. Those are both 1 from above. And if you look at this, I hat and j hat, they're always at 90 degrees, and the sine of 90 is 1. And so the magnitude of the cross product between any two unit vectors, I hat, j hat, and k hat, is either going to be 0 if it's the same vector, or it'll be the magnitude will be 1 if they're different. If you use the right hand rule, you'll find that I hat crossed into j hat gives the direction k hat, and it has magnitude 1. So I hat crossed j hat is k hat. It's useful to develop a little multiplication table here. I hat cross I hat, j hat cross j hat, k hat cross k hat are all zeros, so it's 0 on the diagonal. And any vector crossed into itself, whether it's a unit vector or not, but any vector crossed into itself is 0 because it makes an angle 0 with itself. And the sign of 0 is 0. The other vectors, cross products of these unit vectors, you can figure out using the right-hand rule and the fact that the resultant has to have magnitude 1. But you get this little multiplication table. If you look at it, it's anti-symmetric. If this is k hat, then over here is minus k hat. If this is minus I hat, this is j hat, I hat minus I hat. Sometimes that's useful to know that or be able to generate that multiplication table pretty rapidly. You may have seen this expression. It's a way to compute the vector cross product of any two vectors, and you form the determinant. And in Cartesian coordinates, you put I hat, j hat, and k hat along the top row. And then whatever the first vector is, you put its x, y, and z components on the second row. And then the second vector, you put its components, x, y, z components along the third row. And then you expand this determinant by minors across the first row. And when you do that, you would get something that looks like this. Now you may not have had expanding determinants or evaluating 3 by 3 determinants like this, or used by minors, etc. So if that's Greek to you, you'll have to just remember this expression here and refer to that. The vector cross product is very useful and is very is occurs over and over again, so it behooves you to put in some study time and learn that the vector cross product and be able to use it in subsequent work. You're going to be seeing it over and over again. If you haven't, if you you see it in statics, you'll see it in dynamics. If you go into electromagnetic fields, you're going to see it there. So it's hard to get away from vector cross products. You just have to bite the bullet and learn it once. Also, what I usually recommend to people while you're taking your math, I would strongly recommend that before you take Math Physics 1, to take from the math department, take the linear algebra course, and you'll learn about matrices and in a fair amount of detail and determinants, generating eigenvalues and other things that you'll get a quick review of or a quick presentation of in Math Physics 1 and lots of practice on, but it serves you well, I think, to take that linear algebra class if you can fit it in. And the other thing it does is it helps you get a minor in math, which is pretty easy to do because you have to take so much math anyway in our discipline. So anyway, that's just some advising that I generally give my people that I advise